So with that, it is my absolute pleasure to introduce Klaus Mølmer, who will tell us about quantum trajectories. Thank you very much.
Thank you very much, Gabriel. Thank you very much for the kind invitation to come here. I was invited to give a talk, and I apologize that the title you see here is different from the title in the program. But then after submitting my title, I was kindly offered the opportunity to give a tutorial. So I changed my title and also the content of the talk quite a bit. So I'll be talking about something called quantum trajectories, something that I collaborated with colleagues and others introduced in quantum optics in the early 1990s. And actually, I'd like to share with you this slide because I was here in Rochester 30 years ago, quite precisely, talking exactly about the topic that I'm talking about today. This was my first invitation to a real big conference, and it's nice to come back and give a tutorial on essentially the same topic. Our version of quantum trajectories, we called Monte Carlo wave functions, and this is just pasted out of the PDF version that's available from the proceedings of the conference 30 years ago. And I also want to show you a picture that I had made that I found very illustrative of what we're talking about, and you will see it later in my talk today. So this is a picture of atomic level scheme and sunglasses and photon detectors. They will hopefully all make more sense a few slides into my presentation. So I have a really warm heart for Rochester, although I think I was actually not back in the meantime. So it's great to be back in Rochester after so many years. So we are going to talk about the physics of open quantum systems. So an open quantum system is a system that is interacting with its environment. And that interaction is causing different effects. It can cause energy loss, or it can also cause thermalization and heating of the system. It can also cause decoherence of superposition states in the system due to that interaction. And it's also, in many cases in quantum optics, what leads to atomic systems coming into steady state if you have continuous driving of quantum systems. And of course, all these words you see on the left and right are processes that we are studying, and this open quantum system theory is the theory that describes these processes. Okay. In quantum optics, the system could be an atom, and the environment of atom could be the quantized radiation field. So the interaction is the one that leads to emission of photons, the spontaneous decay of atoms. But it could also be a cavity mode, which is being relaxed because of absorption of light, either through the lossy mirrors or just leaking out of the mirrors of such a cavity. And in modern times, we have in quantum information and computing so many quantum systems that we are trying to control. For example, the qubits in a superconducting quantum computer. So these are electronic components, so to speak, but they are perturbed by electromagnetic fields, by phonons in the substrate on which they are mounted, by spins that are sitting in the substrate that cause magnetic fields to fluctuate with these components here. And also if you have spins that we will also hear about in talks tomorrow at this conference, wonderful spin dopants can act as qubits in solid state, but they will also be affected, of course, by fields in the environment, phonons and other spins in the environment. So it's really a broad field, and I'm teaching quantum optics course, and I tell the students, now you have to listen carefully. This open system dynamics is always and forever going to be important in quantum physics. And it's important because we can never really ignore dissipation and damping in quantum optics and in quantum computing. And the reason why we can never ignore it is the weaker it gets, the better we are eliminating, the more greedy we become. If you have a qubit that can keep its quantum state with 99.9% chance, you are going to work with 1,000 qubits, right? And if you have a quantum atomic system who has a lifetime of 10 seconds, you want to operate it for 10 seconds or 20 seconds. So we will always be hammering our head against dissipation together with our Hamiltonian in these quantum systems. So that is why a general formalism of that is, of course, necessary. And don't worry, we, of course, have these formalisms. I'd like to go back to very early history just to motivate the atom again. So here is the Niels Bohr model of the atom, where we have the classical orbits, and it's interacting with light. The atoms are decaying, losing their energy due to the emission of photons. So that's exactly this interaction with another degree of freedom. And as we heard this morning in a wonderful presentation, Einstein in 1917 gave us actually the physical picture and even the rates for these processes in the Bohr model to take place. I find this absolutely astonishing and fantastic because this is before quantum mechanics, right? So quantum mechanics came in 1926 with the Schrödinger equation, but Bohr could get the energy values right, exactly in agreement with the Schrödinger equation, and actually Einstein's A and B coefficients are also untouched when we later get the full quantum description. That quantum description now goes really into my previous slide. There's a quantum system, the atom. There's another system, the environment. And that's the quantum theory of light we have been invoking here. So this is Paul Dirac, 1927. For every mode of the electromagnetic field, you can think of it an equivalent oscillator, quantum oscillator, describing the excitation degrees of freedom of this oscillator mode. And this is, of course, also the number of photons in this particular mode. And the Wigner and Weisskopf theory that we also heard about today, actually in several talks, is just, not just, it's a formidable calculation, but it's actually solving system plus environment, where the system is the atomic system with ground and excited state, and the environment is these many oscillator modes sitting here. And when Wigner and Weisskopf solved that, and I'll come to that on the next slide, then I refound Einstein's A and B coefficients, as we heard about this morning. Now, the essentials of the Weisskopf and Wigner calculation, and now you see the picture from my 30-year-old talk in Rochester, is to have an atom who is in a superposition of ground and excited state. So this is a picture. This is coefficients A and B for being in the ground and excited state. And I write here the wave function of everything, because this is not yet everything, but now it's everything. This is the atomic state, and 0 means the atomic state and no photons, right? So this is the initial state that we are looking at here. And then as time evolves, there is a possibility for the excited atom to emit a photon, okay? So that means you're going to have a certain amplitude of this state is maintained, but then there's going to be a certain amplitude also where the atom is in the ground state and there's a photon flying away. I apologize for my drawing skills. They're not much better today. And this is such a small blob down here just to reflect that the probability of sitting down here is small. You still have the main probability as you had before for sitting in the original state. And of course, in the formalism, I can write the same thing. It's going to be a sum over all the possible directions and frequencies of that photon. So there's a sum over this index lambda. There's one photon in that mode lambda. And then the atom is definitely here in the ground state. So this is the expansion of the wave function that Wigner and Weisskopf would be looking at. And then they would solve the Schrödinger equation. Not exactly for long times, but they would do a kind of second-order perturbation theory, seeing how these guys would evolve to first order, coupled back to that guy who would then have an evolution with time. And that evolution in time leads to the formal description of this system. If you just look at the picture here of the state, or you look at the quantum state as it's written up here, it actually consists of a 0 photon part and a 1 photon part. And if you're only looking at the atoms, you don't really notice if there's a photon present or not. But the total population to be in the ground state is the incoherent sum of that population and that population. They really correspond to 2 orthogonal states of the field. So the total population is not interfering, but it's going to be the sum of that population and that population. And the same is true for the excited state population, and the same is actually true for the coherences in the system too. You're not going to get cross terms. You're going to get the weighted sum of what this guy says about the atomic state and what this guy says about the atomic state. So this idea of taking different wave functions and adding them incoherently together, that is the thing that we do with density matrices. So instead of using the amplitudes Ci of a general Hilbert space wave vector, you're going to construct populations and coherences. So there will be the Ci absolute value squared, populations, and there will be coherences. And these quantities you can actually add with probability weights corresponding, for example, to those two sides. And that is what we call the reduced density matrix. It's formally the same as making a partial trace over the field degree of freedom of this full state. So that's a mathematical expression of what we're talking about. But you can also say I'm just adding populations corresponding to different states of the radiation field. So what Wigner and Weisskopf did was not only to observe this thing, this is actually a little bit later we start working seriously with density matrices, but they calculated what is the weight, probability weight of sitting over here versus sitting over to the left. This little blob here is drawn a little bit smaller than over here because all the loss into that state came from the excited state component. So you have a new relative population of ground and excited state, both in this 0 photon component and obviously also in the 1 photon component. Now, what came later, and really seriously up into the 60s, was the derivations of what we call master equations. And that's actually nothing but an equation of motion for these matrix elements, rho ij, sitting up here. So there are populations of the excited state, and actually that's where Einstein's A and B coefficients exactly come in and tell us that there is going to be a decay of the excited state population feeding into the ground state. But there's also going to be the effect of Hamiltonians, that we know how they work with the C elements, but they will also have a deterministic evolution then of these rho ij elements. That first part is completely Schrödinger equation-like, but if you want to write it for the density matrix, you get the commutator with rho instead of H acting on psi. So it's the same thing as the Schrödinger equation I put here, but then in the box I have put here this general form of all these damping terms. And you might say, this looks a lot more complicated than what I just said, and that is true, but this is a remarkable result. It was found empirically for every single case where people were writing around this equation, but it was proven in the 70s by Lindblad, Giorini, Kosakovskaya, and Sudarshan that this equation always has to be written on that form, or can always be written on this form, if you want the density matrix evolution to be continuous, linear, and to keep only positive probabilities. Right? So there's a mathematical theorem who says that you can always bring all these A and B coefficients, say, on a formal form like this one. Okay, I did not know about that. I did when I gave the talk 30 years ago, but I did not know when we started working with these master equations. But it's actually an extremely useful result for the quantum trajectory story, because it ensures that everything I tell you from now on applies to all master equations on this allowed form, on this permitted form. Okay, so I hope you follow me that when you have these open quantum systems, that you can have any unitary dynamics going on, but you can also have these exchanges with the environment, and they have a certain operator form, and we know how to solve these equations. So Monte Carlo wave functions, quantum trajectories, I'll show you our version first, because it's the one I know the best, and then I can use my old picture from my talk here. So I just go back and show you exactly the same equations again. And then I told you before that, well, in fact, we are looking now with sunglasses, so I can incoherently add those two things. There is another option than adding those with the corresponding weight factors, and that is simulating this system and picking one or the other one. Okay? So if you are in the lab, for example, and you don't wear sunglasses, but you have a photon detector, there will either be no click or a click. And if I have this quantum state and I detect 0 photon, then our system is projected onto the wave function on the left, this one. And if I see a click, then I'm projected on the right-hand side in which there was 1 photon, and that's the ground state of the atom. So our insight in '92 was that this master equation, and also of the more general forms, can always be simulated on a computer, for example, just by picking either of those two choices. And you do that at every single time step dt, and then you get a quantum dynamics, which is consisting mostly of a smooth evolution, renormalizing, because after every measurement you have to renormalize the state, or these quantum jumps into the ground state. And they're, of course, also very physical and intuitive. You have a photon click, and where is the atom after the click? It's, of course, in the ground state, because it has just emitted that photon. So this is a pseudo-derivation for you, actually, of this simulation method. And we can prove that if you do that stochastic simulation, you're going to get, on average, over many trajectories, exactly the same as the master equation, because it's exactly what the master equation already does. So it's adding these things, but now we can throw dice to find out what we should do with the wave function. So the evolution in the green part is slightly modified. This is the general form. In general, in this particular case, it's the same as giving a small imaginary part to the excited state energy to represent the loss of population who goes into this state over here. So there's a reduction here, followed by renormalization, and that reduction is generally, in the general form, described by this non-Hermitian Hamiltonian. So you have to solve the Schrödinger equation with a non-norm-conserving Hamiltonian, and then you have to renormalize afterwards. And we call this the no-jump dynamics, because there was no detection. It was the no detection event. And then alternatively, there is the jump dynamics. And here there's actually, if the general many operators here who describe different dissipative channels, then you have to pick one of them. So any one of them is picked. Either you act with L1 or L2 or L3 if there's many of these operators. In the two-level atom, it's just a step-down operator. So you act with a step-down operator on your state with a probability, and all these probabilities are known, and actually their values are just given by the mean value of this L dagger L. That's exactly the amount of population you lost in the no-jump dynamics. The full dynamics conserves, of course, the population here. So it's a very simple recipe, even for the most general of master equations, to tell what you do: evolve a wave function or jump the wave function with rates that we also know at any moment in time. So it's a quite easy to do method. So we called it Monte Carlo wave functions, and we being Jean Dalibard and Yvan Castin and myself, we had only one application in mind, and that was to simulate master equations using wave functions instead of density matrices. okay? We were happy to have a physical motivation for why it looks the way it does, but density matrices are n times n, where n is the dimension of your Hilbert space, and the state vector is only n times 1, because it's a column vector. So we would save on the dimension of the object, and I'll show you an example where that is a worthwhile that saving. And in fact, in modern times, people are using this method simulating quantum registers in quantum computers with many degrees of freedom, and the Hilbert space can be so large that you really don't want to work with n squared, but you are happy to work with dimension n of your equations. Now, I'll show you two other motivations, which in exactly the same year, completely independently, and I would even say before our work, were promoting the same idea. So one was Howard Carmichael, fantastic physicist, huge format. He did not publish 10 articles. He published a book about this method. He gave lectures in Brussels, and we saw his lecture notes, and this nice thing came out. You can download it from the Springer, and it's a wonderful, wonderful thing. It doesn't come with pictures of my daughter inside, but I kept her pictures inside this book because I always had the book with me, and then I would always bring her picture also along. So Carmichael's philosophy was not to simulate the atomic dynamics. He was not interested in atoms. He was interested in light. He was interested in understanding the fluctuation properties of light. If you make a detector signal, it's clicking all the time, and there's statistics in those clicks. How does that statistics come about? And what Howard realized was that you're not going to model that by a simple classical click model. That had been proven that you can't do that by Glauber and others, or at least hinted at. He realized you have to evolve together the atomic state and the signal record, such that the state gives the probability for a certain signal, and when the signal happens, there's also a back action on the atom. There's the jump into the ground state every time you hear a click. So you have to have a state vector who evolves according to the record, and you have to have the record evolve according to the state, namely Born's rule for what you measure on the system. So brilliant, fantastic. I mean, much more deep thoughts than our idea, but it's exactly the same procedure, same protocol, that you are evolving a state together with a simulated signal. Beautiful, beautiful, beautiful. And then there was Gerhard Hegerfeld. This is a kind of tragic story because Gerhard Hegerfeld was also doing Göttingen in Germany. He was actually doing this the same time as us, and maybe even earlier. And he had a paper rejected in PRA. Shame on you if the referee is here. Because that was a brilliant paper, but it came out as a conference proceedings. So he knew about these kind of experiments where you have single ions here, there are 5 of them, in ion traps, and they have a shelving transition. So you can have heavy fluorescence on a 2-level transition, but then sometimes it goes completely dark. And that's because there's a transition, either via excited states or via a weak drive, that can put the ion, or the electron actually in the ion, in this shelving state. And then you are dark for some while, and the signal comes back again. So this is what you see with your naked eye. This is real time, and you can see it in a dark lab. Thousands of counts per second, suddenly no counts per second, and then many counts per second again. How are you going to ever describe that by master equations, who are deterministic and smooth? This is clearly a random signal. But actually, this method that we just talked about, tossing coins, will exactly reproduce these kind of records. So that was the insight by Gerhard Hegerfeld, and of course, many of his students and colleagues later on developed these ideas much further. So I write to you again here the master equation, which has a general form. One of these could be decay into the ground state. Others could be decoherence, could be heating from a heat bath. Einstein's A and B coefficients could be all over the place here. For superconducting qubits, there will be a number of terms here also. And here's the Monte Carlo wave functions again with a jump and no jump dynamics. It's already now in many textbooks on quantum optics because it's extensively used for simulations. If you have an old state vector code, so you already solved the problem without the environment, it's super cheap to add the environment and just solve this. You see, you just already have the Hamiltonian and this dynamics coded. You just add this extra non-dissipative term to your code, and then you're actually taking into account dissipation. Exactly, right? So it's very cheap if you have idealized the system and then you want to make it less ideal, to transform into that. And then, of course, it's also part of numerical libraries like MATLAB, Python, Julia. So I just want to tell you that there are Q-tip solvers for Python and now also for Julia. There's a quantum optics package for Julia, and there are quantum optics toolboxes for MATLAB. Here I just show you what the Q-tip looks like. So the master equation comes in Q-tip with a command called master equation solve, where you just have to give the Hamiltonian, the initial state, and these operators who are actually the L operators. Okay? And if you want to do the Monte Carlo solver, you just ask the same package MC solved, Monte Carlo solved, Hamiltonian initial state, the operators, and then this guy is often set at 500. That means it does 500 trajectories. And then you're disappointed because you get smooth density matrix evolution. It shows you already the average. But if you put it equal to 1, you'll see the jumping stories. So that's a funny thing. And then the SSE solver, I'll come to that in a second. That's under a different measurement model. And there are also hybrid ones where the system is monitored, but not completely. So you have a mixed state density matrix, which is stochastic because of some measurements you do on the system. And that's also sitting in QTIP. It's called stochastic master equation solve. So it's really nice. I mean, we don't even have to write these codes anymore. They are already written and super, super user-friendly. So what are the lessons we learned by using this method? Well, I learned a lot. I once gave a talk where I said, oh, this is fantastic, you learn so much. And then there was a big grumpy professor in the room, no names, and he said, this just shows how little you understood of the physics. And I could only say, yes, you're right. But now I understand it better, so at least we can be happy about that. So first of all, I'm a Danish, right? So I'm extremely proud to have actually brought Niels Bohr's quantum jumps back. I mean, and I'm not even just joking about it. Niels Bohr made the quantum jump theory. They disappeared. The Schrödinger equation is continuous in time. He wrote a very worried paper in 1928 about where did the jumps go, and are there still not these discontinuous elements? And the answer is no. The Schrödinger equation is a differential equation, except one element in quantum physics, and that's the measurement process. The projection postulate is discontinuous in our ideal description of what is a measurement. But so you see, the Bohr's quantum jumps are back, but it's the opposite story. It's not such that the electron jumps and emits the light. It is us detecting the light, and therefore we jump the state. It's the measurement back action, but still, it's the quantum jump. So here is actually the simulation for a two-level system, which is driven by a laser field coherently, and it does what's called Rabi oscillations. You're used to seeing, oh no, you're not anymore, but we were used to seeing damped Rabi oscillations when we solved the master equation. And these damped Rabi oscillations come about because of the decay rate of the atom. But actually, what you see if I do wave functions is they are not damped, they are full contrast. And then they jump, and then they start a new full contrast. So in fact, these single atoms sitting in the laser field, they don't fall into a steady state. They go up and down all the time, and they go full contrast up and down all the time. So actually what I always thought, or what I think we normally describe as damped Rabi oscillations, are actually more out of sync Rabi oscillations. Because when you do the average of many of these trajectories, then you get what looks like the damped Rabi oscillations. I think that's a nice little insight. It's not the deepest thing I ever realized in my life, but it's still a funny new picture on this. So the picture here actually shows the dotted line is the master equation, the solid line is the average of 100 trajectories. So there's a role also of the no jump dynamics, which we see many, many places. I won a pizza from Marlon Scully once because I could explain something that you said you can't, and we could. There's a lot connected to Zeno effect, dark resonances in spectroscopy, where we can actually understand that it's the no jump dynamics that is for making the system populate certain states. Very, very exciting. Quantum optics insights, I mean, just coming back, Carmichael and Hegerfeld had much deeper ambitions in actually understanding the origin of signal correlations in optics, or understand dynamics of atoms, which is now just coming out, staring into our face. So I think that's very nice. And modern times, because this was 1990s, and there was nobody monitoring the single quantum system with high efficiency. Today we do it all the time. All the quantum systems we use for quantum computing is not an ensemble of thousands of qubits, it's one qubit. It's a register with 100 bits, but it's not a million registers with 100 bits, it's one. So therefore, this dynamics suddenly becomes the dynamics of a single monitored quantum system. So I think that's also very, very important. So let me just give you a few examples from the numerical side. So I just showed you already, there's 100 wave functions there. Actually, what I really want to show you on this slide is that the way to calculate anything is always calculating a mean value or something. This is showing the excited state population. So that's the mean population of the excited state. And any operator you want to estimate what is its mean value, by which I mean the mean value with the density matrix, you just take the wave function mean values and average them. So if you have 100 wave functions, you have 100 candidate values for the mean value of any operator A, and then you just take that mean value of those mean values. And then there'll be an error bar, and that reflects, of course, that you have a finite ensemble. So your error bar will go as 1 over square root of the number of realizations, just like in experimental physics. Here we're doing 3D laser cooling. This is actually why we did this, because I was doing laser cooling for my PhD, and in full quantum descriptions, the dimension of the Hilbert space would be 3 times 10 to the 5, and I didn't want to go to a density matrix that would have 10 to the 11 elements, but now with wave functions, we could actually do these wave functions. So here's a momentum distribution. I just plot it because it's fun. Here's temperatures as function of the intensity over detuning of the laser field. So there was an idea that there would be general scaling laws for different types of atoms, depending on which Zeeman levels they have in their ground state. And we could actually verify that there's a minimum and there's this scaling law present. In this case, we had only 20 wave functions. But these are systems who are in steady state. So there's an extra possibility to gain precision or to remove fluctuations, and that's by averaging over time. Because wave functions never reach steady state. So if you average their time evolution over time, there'll be a kind of ergodic principle saying that then you will also get the mean value. So it's fairly cheap for systems like these to use only few wave functions and get very small error bars. Here's a completely different story. Maybe Chris will talk about that in his ion trap talk during this conference also. So there's a gate between 2 ions where you use the motion as a data bus. And my fantastic student, Anders, came up with a proposal, and we wrote a few papers on how we could eliminate that motion completely in an ion trap gate. And what is shown here is how the internal state forms a maximally entangled state. So this is ground, and excited. And this is the superposition of both being ground and excited. And that's created in the density matrix language, and here averaged over 50 wave functions perfectly. So this was a case where we had this idea that even though there's a master equation, damping of the motion, Einstein A and B coefficients heating the oscillator, we would still do good gates with 50 wave functions. It's fun to run just one, because if it works well for 50, it should probably also work well for every single one of them. So here is actually just one trajectory. And what I just want you to notice is, first of all, that, yeah, it seems to go very well, but down here, every single arrow is actually a hammer hitting the harmonic oscillator, adding a quantum of energy or removing a quantum of energy. And you can see the internal dynamics is essentially unaffected. And that's exactly the idea of Anders Sørensen in this gate proposal, that we would be insensitive to that. So having this single wave function that you can run is just very illustrative. If you want to be robust against something, you can run just one trajectory and see if you're robust against this or that. So that's a more modern application of these ideas. Now, I just take a little intermission here to talk about this standing on the shoulders of giants here. So, of course, there has been many, many ideas about these things around. There was a photo detection theory pioneered in the 60s and leading to the quantum optics revolution, where people definitely had a lot of insights about emitters and what emitters have to do when they have emitted the light. This anti-bunching feature, which is completely equivalent to the atom going to the ground state every time a photon is detected, is lying in these papers. It's just the formalism that is essentially missing. Then in the 1970s, there was actually work done that was exactly equal to what we did later. Particularly one of my heroes, Slava Belavkin from Russia, but Hudson, Patasarati. These were people who were inspired. Well, Belavkin was maybe instructed by his supervisor, Stratonovich. So he said, dear Slava, please, can you make Stratonovich and Ito calculus for quantum systems? Okay, so these guys have made stochastic differential equations, mostly for classical systems, Brownian type motion. And then how would that look if it was a quantum system? And little Slava, he did as Stratonovich told him, and he actually developed stochastic quantum evolution. Okay, he was not in the literature of quantum optics, but he wrote equations that are identical to equations that we wrote a decade later. So we just were not aware of that, and of course we got in contact. He approached us and said, you know, I have already done that. And this was one of the cases where the Russian had actually really done that. So he had, and he was a fantastic, super nice scientist and a genius scientist. He visited me for half a year in Denmark, and we did single work together. And even after having been in my office for half a year, he still referred to me as an experimentalist. Right? So there was a conflict or a culture difference between mathematicians and physicists. And then there were extremely foundational ideas, also in the 1980s in particular, and the end 70s. Girardi, Rimini, and Weber from Italy were proposing to add stochastic terms to the Schrödinger equation as a way to have collapses of big wave functions happen all by themselves. so that there would not be a measurement postulate, there would just be a term in the Schrödinger equation that made big systems, like the arrow on your real apparatus. That can only be classical. Even though it's a quantum object that couples to the quantum system, because it's so big, it will, due to this stochastic term, localize. So these equations existed. Penrose and Diossi had ideas that could come from gravity. Chizin had some work related to what's his name? People from particle physics theory also. And all these people introduced stochastic term and stochastic evolution of wave functions with different purposes. These mostly with the hope that they could replace or remove the measurement postulate in quantum mechanics. And I was very fascinated because now finally we got to know about these works because they approached us and said, you know, we also have something like that. And I actually went back and I wouldn't say I attacked these guys, but I demolished a little bit the purpose of this thing because we realized that these stochastic equations are also completely compatible with measurement back action. So I just remind you again, this nice little drawing you see, I use it all the time. The atom emits and you detect the photon. There are other ways to detect light emitted from an atom. You can have the atom emit some light. You can put a semi-transparent mirror. You can mix with a very strong beam from the left. And then you can have detectors who count the interference signals up here. You will still see all these photons, but they will be mixed with the classical photons coming from this local oscillator. This is called homodyne detection. So there will be an interfering amplitude, which is the sum of the C number term beta coming from here, and the annihilation operator corresponding to the photon that actually comes from a real atom going this way. The intensity is going to show a big boring constant intensity from the local oscillator, and then an interference term, and this is why we say that this is a way to measure the amplitude A plus A dagger of the field. If you do many, many clicks, then the jump operator will not be A removing the photon from this source, it will be beta plus A, which is predominantly just taking photons from the classical field, but of course also with a small amplitude taken in from there. So you can see the effect of this thing is actually infinitesimal on the atomic state. It's completely dominated with beta, which is beta times identity. So you don't do much except a little bit of change of the atomic state. So in this process, homodyne detection, you measure signal all the time, but the atomic state is not jumping to the ground state, it's jittering around. On average, it will decay exponentially to the ground state, just like in your trajectories from before, but it's a completely different story. It's a quantum state diffusion type model. And it's actually the same equation as the GRW equation and the equation that Chizin had written down. And of course, Belavkin had also written this equation down in his time. So instead of having the jumps, we now have a density matrix or a wave function who has a little Schrödinger type term that's linear in dt and a little noise term in a Wiener noise that I call dw here. It's a little noise term. So interesting, the jumping or the jittering. What happens in real life if you're not looking? Well, I'm from Copenhagen, so of course nothing happens in real life in quantum physics. The only thing that happens is what you see. So you have to look at the system, and then if you look by a counter, this is what happens. If you look with homodyne detection, this is what happens. And the reason that it is like that is because the atom is actually emitted with the radiation that it emits. And it's actually an EPR-type paradox situation we are in, because when I do a measurement of the photon, I decide which basis I'm collapsing the atom in. So it's very much like the normal Einstein-Podolsky-Rosen story. So not alone did we revive Bohr's quantum jumps, we even made them happen in a way that's complete agreement with this Copenhagen interpretation, and an illustration even of that aspect of quantum theory. So a master equation just once more, the trajectory is once more, I showed you a few times. I'd just like to point out that, of course, when you do this kind of work, you realize that there's already been people writing down, not exactly these equations, but something very similar. There's been a long history about measurements and general dynamics in quantum systems, something called the Klaus maps. So this is not a particular physical operation, it's just, I don't know where the rho got, but the density matrix will always have to evolve into something of that form to preserve its positivity, where these guys add up to identity. This is in complete agreement with this guy, but this is a pure formal argument made by Klaus and others. And the quantum trajectories, they correspond to each of these being realized as being a general measurement back action operator. These could be projection operators, and then you have your good old textbook quantum mechanics. What happens to a state in a measurement? You apply a projection onto it. But they don't have to be projections, they can be more general. So the more general outcome is that rho is replaced by m rho m dagger, or psi is acted on by these general matrices m. And I just remind you that in my jump, no jump, I don't have two orthogonal alternatives. Either I keep a superposition or I jump into the ground state. So these two states are not orthogonal. The orthogonality was it was a 0 photon or 1 photon component. These are orthogonal photon states. That's why I could distinguish them. But the atom is actually acted upon by these more general back actions during these measurements. So there is a formal equivalence. And I would say that when I learned that, then I'm just as often referring to this kind of evolution as to the master equation when I'm talking about what a quantum system is doing. It's acted upon by these operators. The evolution is the action of these operators. So on the left, you have what a physical system forces us to realize. There are damping rates, Einstein A and B coefficients. On the right-hand side, you have a more formal description of what any dynamics would look like, whether it's open system dynamics or it's you measuring on the system or whatnot. So it's more a general theory of measurements, errors in a quantum computer, attacks by eavesdroppers, or whatever you like to model, where somebody is attacking your quantum system one way or the other. But the two formalisms are very, very equivalent, and you can just recognize them in one into the other one. So I'd like to show you an example, a very famous example from the physics literature of this story. This is a microwave field being your quantum system between two mirrors. It's Serge Roche's experiment in Paris. And he's probing the microwave field by sending atoms through this field. And when the atom interacts with the field, it doesn't absorb the photons, but it has an energy shift, an AC Stark shift, which causes a phase accumulation on one of the two atomic states. So when the atom comes out, then it has shifted to an orthogonal state if there's a photon in the cavity, but it has remained if there was no photon in the cavity. And here you see how the atoms predominantly come out in the same state as they entered, so there was no photon in the cavity. But sometimes they have predominantly switched to the other state. That's because there was one photon in the cavity. And this whole record is given this fantastic title of the Nature paper by Roche, Watching the Birth and the Death of a Photon in a Cavity. So instead of having a Boltzmann distribution all the time, you're actually fleshing those probabilities into how big fractions of time do you have 1 photon or 0 photon. And that is what is happening when you measure the photon number in the cavity. You're going to see whether it's 0 or 1, but there'll still be a Boltzmann distribution, but now it's going to be reflected in what's the probability to see one or the other of those two possibilities. And then he did it again, but this time it was not a pi phase shift, so now you're not orthogonal. Now there's pi over 8 phase shift, so actually the atom comes out undisturbed with 100% chance if there's no photon, but it is undisturbed with smaller and smaller probabilities if you have up to 8 photons in the cavity. So in this case, it takes also a few atoms going through to tell what is the actual photon number in the cavity. So in this case, you start out uniform, and after some time, the trajectory has taken you to think that there are 7 photons in the cavity. Next shot, 5. Next shot, 4. Next shot, 3. The average is going to exactly correspond to the initial distribution. And here they 10,000 atoms through the cavity. And then they learn that now there was 5 photons, and then bloop, suddenly the most dominant probability is 4, 3, 2, 1, 2, 1, 0. So here they learn how the atom number is going from an initial state gradually leaking out of the cavity, counting essentially not the photons, but counting via the atoms how many photons are in the cavity. This is also what I would call a quantum trajectory, because it's actually a quantum phenomenon. We are learning what is the quantum state of the system. This is the formalism of all these M operators I wrote before. The state is evolving under action of all these. Every atom is a measurement. Every atom gives you a state. And then finally you ask, what's the probability of having n photons in the cavity? And that is plotted here. Okay, there's also been ideas to use feedback, and there'll be talks at this conference about using feedback. So this is the quantum lion tamer who is looking at the atoms and says, I want a certain number of photons in the cavity. And then you do a correction action. So in this case, they have now equipped the experiment with the possibility to go back, inject atoms resonantly, and put photons in the cavity. And here they wanted 4. So you can see that they essentially have 4 all the time. Sometimes they are losing ones. That's because now these atoms are wrong, have the wrong statistics, and then they inject an emitter atom so that they can raise the photon number, or they inject absorber atoms so they can remove a photon from the cavity. So this is a way, very direct, to actually use the trajectory to inform what you should do. And I should say, of course, there's much more advanced work going on in these directions. This is monitoring of superconducting qubits, and I would like to acknowledge, actually, there's beautiful work done by Sasha Korotkov, Andrew Jordan, who is here, Yuli Nazarov at Delft, who did not use the quantum optics methods because that was not their culture, but who developed a very similar formalism, not in full, but I mean very close to what we were working on, more under the name of a Bayesian analysis. So if you shine a microwave field on a cavity with a superconducting qubit, the reflected signal will have a phase that depends on the state of the qubit. It will be a super noisy signal, but every little piece of that signal will inform you whether you had this qubit in one state or the other. So here's plotted the calibration curve for such experiments, where if you are in one qubit state, you have this distribution of measurement signal. If you're on the other one, you have the blue distribution. And that actually means that if you do any measurement, for example, here or here, then you will with high probability be able to say that was a measurement of the qubit state in the cavity. In real life, using our formalism, you would say during the measurement record, you measure all the time, and your quantum state is in one experiment very quickly becoming the readout of the qubit in state 1. This is another trajectory, same initial state, just another random realization, and here you end up being in the other qubit state, because half of the time you will end up in one and half of the time you end up in the other one if you start in the 50-50 mixture. So this is how these trajectories look, and where you could consider, can we use this for something? And that's of course the way we describe these experiments now. This community is now the best quantum optics community. They outperform many quantum optical systems because of the large degree of controllability here. And there's a beautiful, I just go to this next slide here, beautiful experiment of feedback again. So now you can take the signal coming out from that qubit, and then you can say, I'm not happy that my qubit decays. Let me leak in some field to put it back in the excited state again. Or I'm not happy that the Rabi oscillations are damped. Let me put in some field so I keep them undamped forever. So you can now keep qubit states alive forever in a known quantum state. So you could also just wait and create it again at the end, but at least these protocols are now nicely working. And just to acknowledge, Howard Weissman and Milburn really had a long project that came to fruition together with these trajectory methods on feedback in quantum systems. So really brilliant. Now, I don't have so much time left. I'd just like to tell something that we've been working on a lot in the more recent years, and that is just a question I had for myself. I showed you Arroch's experiment. He's measuring all the atoms. He gets a measurement record. What is the state of the atom? He concludes what is the state of the field, and that's, of course, very nice. But when he published the paper, he already knew also what was these later measurements. What were these outcomes? But he never used these outcomes to say anything about the state of the field at this earlier time. Okay. In daily life, if there's something you're looking for, you're happy when you find it. But typically, you also know where it was before you found it, right? If I'm looking for my car key, as soon as I find it, this is where I should have looked already in the first place, right? And then I say, oh, I will yell at my wife. I say, the car keys was in the kitchen. She said, sure, it's been in the kitchen all the time. So when you do measurements in daily life, when archaeologists make a find, they don't change history, but they learn things about history, right? So why don't we have the same situation in quantum mechanics? Why should I not use all measurements to infer what was the state at this earlier point in time? And I was thinking about that for a long time until I realized that it was actually more difficult to find the good question than turned out to be harder to find the good question than after that we could actually answer it. The right question, because it's quantum physics, is a difficult one, because there is no such thing as a true state. I mean, quantum is just so weird. So we cannot say there's a true state. State is not something really existing in our world. It's a description of the system. But what is existing in quantum mechanics is outcomes of measurements. And what we do as theorists is we predict the probabilities of outcomes of measurement. So I realized that what we should do is actually use these early and late measurements to retrodict the probability that an outcome at that point of some measurement would have had a certain value. So somebody sneaks into my lab while I'm out for lunch. I measure on it after lunch, I come back, and now I can guess what he or she got when that measurement was done during the lunch break. And I want to use the before and after measurement. So I will not go through the formalism. It goes exactly through this POVM operator things, and I'm accumulating a joint probability for all the events. But the trick is that if it's a measurement happening in the middle of the measurement process, that's where it is sitting, because it has a measurement back action when I'm away for lunch, and then I do measurements later on. And the probability for this joint series of outcomes is given by this expression, but that actually means that the relative probability for any outcome in the lunch break is just given by the same formula, and these guys are fixed to what the values I know they had, because these are my measurements that are sitting here. So I'm sorry, I'm a little bit quick on this one. I just want to show you how it worked when we applied it to Serge Arroch's experiment. So this is what I showed you already. And then I talked to Serge and said, can we have your raw data? Where were all these atoms? Because I would like to use our analysis with our formalism to actually tell you what was really the photon number state. And I got tears in my eyes when I saw this thing. I'm a little bit sentimental about physics, I have to admit that, because it looked like that. There's no cheating, no fooling around. This is just the same 10,000 atoms in the same experiment. And what is seen here is the probability of having 5, 4, 3, 2, and 1 photons in this cavity. And there's really two things that are happening here. One thing is that every moment in time, the measurements just before and after, they both contribute to your knowledge. So you have essentially a doubling of the signal to noise. And all the little spikes, they're just spurious. But how can you know it's spurious? You could seriously be on your way down here to the lower photon number, but then the statistics recovers. So it was actually just a spike where you had maybe 5 atoms in the wrong state, right? But you know, of course, afterwards. So if you know before and after, then there's no even sign of these spikes here. So I'm not doing it with hand. I mean, this is just a very simple formula that is just telling you what are these probabilities. So the retrodiction here is a stronger assignment to what was the state of the system. And what we have been doing more recently is to apply this to sensing. So we are not trying to retrodict quantum state. We're trying to retrodict what was the magnetic field that was driving the atoms at that time. So we could give a medical doctor, for example, a better way to analyze magnetic field fluctuation due to currents in the heart of a patient or whatnot. The chairman is standing, so I will skip my little session on metrology, but I hope I can convince you that since these are measurements on quantum systems, these are also measurements on quantum probes that act as sensors. And that also means that all the trajectory analysis I've been telling you here becomes also a theory for estimation of parameters by measurements. In fact, we do exactly the quantum trajectories the same way, and then we can extract information about unknown parameters and their time evolution. So instead, I just switch to the last slide, which is not really full of information. Quantum trajectories, there's still many directions to explore. We're working very hard on this sensing business with them right now. I would just want to show you some references and also more recent ones. This is the wonderful book and my beautiful daughter. She's now 33, but she's still my beautiful daughter. This is a review paper we wrote in '96, actually based a little bit on my lecture notes from the Rochester conference also. Beautiful book by Weisman and Milburn on quantum measurement and control measurements have a central role to play. Quantum measurement theory by Kurt Jacobs explains also very well. And then this one, which our students just love, Andrew, so now you owe me a beer later. But this is a really wonderful book to learn about also the trajectories, plus the wonderful physical systems that Irfan Siddiqui and Andrew are discussing in this particular book. So with these, I mean, it's not all new research. This is a method that we are now using throughout quantum optics, but we'd love to disseminate it to all other fields. Thank you for your attention.
Thank you. Thank you very much for the very nice talk. So we are open for questions.
Thank you, Klaus. So it's a kind of a long question, but is back action physical? And I think you're going to say no, because you can tell us that when you have a cavity with photons in it, some photons leak out, you make a measurement. But the light that's still in the cavity doesn't know what measurement you made.
No.
It doesn't know if you measured a photon number or if you measured a homodyne amplitude. So you cannot say that your measurement forces the state in the cavity to be something.
So
there's no back action physically in that sense.
No. And that's true. And of course that rhymes with the Copenhagen interpretation of quantum mechanics, who says that the wave function is not physical. The wave function is a description of my knowledge about a system. The system itself, we don't know what is the state of the system, but I have a knowledge psi, which is actually a probabilistic type knowledge, because that's what we do with psi. It gives probabilities for any measurement outcome, and if you know the probabilities for any measurement outcome, you can also infer what is psi up to a global phase. So the wave function is nothing but probabilities, okay? And when you deal with probabilities, you have a different situation. When you learn something, then you have an abrupt change in your probability measure, right? I have a coin, heads or tails, 50-50. Is that the state of the coin? No. What is the state of the coin? Something completely different from 50-50. There's nothing to do with 50-50. 50-50 is you not knowing what is the state of the coin, right? And now I look and you don't look, so now actually the state of the coin is something I know. You might disagree, but that's not a paradox, just because you don't know what I'm seeing, right? And it was abruptly when I looked that it changed from 50-50 to 100%, and now I tell you, heads. And now bang, it collapsed for all of us into heads. That's a classical, completely trivial thing, which I think is the essence of quantum mechanics measurement, okay, and the Copenhagen interpretation. But we can discuss that from now to doomsday, because there are other interpretations of quantum mechanics, and I acknowledge and I love them, but they have other characters and features to them. Yeah.
Thank you so much for a wonderful tutorial. So when describing open quantum systems, the system is open to the environment, but also environment is open to the system.
Yeah.
In the quantum trajectories, there is only one way interaction that way, that you can only lose excitations to the environment. Can you tell a bit more about whether you or others thought about when you can cancel out the kind of the reverse excitation from the environment, which kind of comes in as noise?
Yes, so beautiful. So actually, we do have excitation from the environment coming in, because we do have the B coefficients of Einstein also. So we actually, the master equation does account for energy going both ways, but of course only in the average sense. And when we do the trajectories, we are simulating the effects of these things going both ways. We are in the Schrödinger picture, and the Schrödinger picture, we would not call it noise, we would maybe call it randomness because of the measurements. But this noise word is something we more use when we talk about observables. The signal is noisy, but that's the same as a quantum error bar, and that's something operators have. That's not something states have. But maybe one thing I would like to say, and thank you for the very good question. The quantum optics program from the beginning was a little bit like the gambit of chess, because we were really interested in the field properties. And then we eliminated the field, and we found only the atomic dynamics. But we were not done yet. It was often called the source master equation. So we got the atomic dynamics, but then subsequently, we actually know how to calculate the field properties. So if you want to know the intensity of fluorescence, it's the excited state population times gamma. And if you want to know the spectral properties of the light, it's a 2-time correlation function of the dipole oscillation that becomes the field properties. So we actually never lost the fact that both systems are quantum systems. We just focused on the smaller one, because then we could express the field one in terms of that. Why was that so much easier? That's because it was a free field. It's actually just given by Maxwell theory. So it's propagating away, as we also heard this morning, there are modes, but they're just Maxwell. And then the field amplitude is governed then by the properties of the emitter dipole oscillations. So we can go and recover the effect of one on the other, but sometimes we do it in a funny sequence where we do one system first and then the other one afterwards.
Yeah, so since you offered to discuss the measurement problem until Thursday, I will ask a question about this. I think you've shown really beautifully how quantum trajectories help us explain a lot of these phenomena. And you also alluded to the fact that the quantum trajectory theory essentially marries, right, unitary evolution and projection.
Right.
So my question is, do you think that there's a path for quantum trajectories and this insight to make predictions to resolve how we think about the measurement problem, or to resolve different interpretations?
So that's a good question. I will not make that claim, because in some sense I have to make the trajectories. I've already adopted to one view on that. I'm using the normal textbook projections. I'm just noting that projection on the field state becomes not a projection, but a jump on the atomic state. So I'm actually doing textbook quantum mechanics. And we were a little bit lucky that it was not already invented in 1929, because it could have been. But then, okay, it was there to be found later. We have not made anything like a Bell theorem proof of anything in terms of relations. I find it fascinating myself, and I would like to share with you that experience, that it stares into my face all the time how consistent everything is. I mean, think about this past quantum state construction. It's such a weird thing, but it's formalism, just the standard formalism immediately gives these probabilities, and it works. That means that I can actually talk about quantum states in the past. They do depend on what I measured later, because my knowledge about the past obviously has to depend on what I measured later, like in archaeology. So that is also part of the standard quantum formalism and the standard interpretation of quantum mechanics. So I feel I lend support to the consistency of the Copenhagen interpretation, but I'm not delivering a proof of the Copenhagen interpretation.
Thanks.
We have 2 more on this side. Any other questions? Here.
Yeah, thanks, Klaus. Very interesting. Let's see. So somewhere in the tutorial you said that it's theorists' jobs to predict, experimental outcomes. But then later, I felt you were contradicting yourself because you were going to retrodict experimental outcomes.
Yes,
right?
but it's actually a little bit funny because in some sense, in quantum optics, we have this culture, we can predict something. And then we are seeing that my prediction fits the experiment. It's a funny obsession. I mean, nobody questioned that quantum mechanics was right. And if you look into other branches of physics, they're more about explaining a phenomenon, not necessarily predicting the outcome of an unknown measurement. We have been there. We have done that since 1926. So in some sense, I mean, I think taking a next step on these quantum systems, you are not interested in predicting the future of a random measurement. You're not going to do 1 billion experiments to validate that anyway. We are going to talk about the physics that actually happened in the system. And then you will get physical pictures. So if I want to work with a sensor, for example, I don't think the medical doctor wants me to predict what is going to be the next measurement signal. I think he wants me to give as precise an assignment of what was the magnetic field from that patient's heart, like in EKG diagrams, right?
Okay, that's fair. But I still wonder, how can you either refute or validate that your retrodictions are actually...
good. Yeah. So then we do the same as we always did. So the measurement in the middle, the one I'm retrodicting, somebody else did it. So actually,
because your retrodiction is a bit different from the experiment.
Yeah, Andrew, you give the beer to Lieven afterwards. This is so fun. I showed you this picture where I got tears in my eyes because of the nice plot. We submitted that article to Physical Review A. The referee said, this is not, I cannot accept that because this looks very nice, but who says it's right? Okay? No. And I was just laughing because, Serge Arros published this in Nature, and they gave him the Nobel Prize. We heard about Nobel Prizes earlier today. They give them for almost anything. But he had never shown that this was right. People were so impressed. Wow, he can track the photon number in the cavity. This is just the graphs. Nobody knows this is right. But down here, okay, so we were right. The referee was right. So actually, we instructed the guys in the lab, please inject, like in the feedback loop, secretly a photon at some point. And they picked atom number 4000 to be resonant and put a photon in the cavity. And when they did that, we had a jump to 1 when they did that. Okay, so we have done that test experiment too, and we have done it with Cater merge on superconducting qubits also. So of course, to validate that these retrodictions are right if you sneak in and do the experiment, of course.
Yeah, really beautiful talk. You're trying to do basically unraveling of a quantum master equation into a stochastic Schrödinger equation, right? So usually it's not unique. For example, I can have gazillion different choices. Yeah. I can, for example, decay my coefficients amplitude deterministically, adding a phase randomly. I would achieve the same thing, probably the better convergence numerical if we actually try this. Yeah. So I wonder, do you think your way to unravel quantum master equation is unique?
No.
That is consistent with Copenhagen interpretation?
No. So in fact, I showed you how the jumps and the homodyne detection are two different unravelings. And none of them are, of course, unique. And I could also homodyne with different local oscillator phases. I can heterodyne. I can split in two and do both counting and homodyning. I can do a million different things. So no, this is far from unique. Yeah.
Then as a physicist, right, you ask yourself probably, is this the way nature operates, right? Usually, nature, unlike physicists, won't have these additional degrees of freedom like gauges and interpretations, right?
Yes. So of course, coming a little bit back to the discussion we had before, so of course, in my little limited Copenhagen mind, I would just say, well, in fact, the theory is not even a theory about how physics operates, but how my knowledge about the system is. And until I do measurements of a certain kind, my knowledge is density matrix. When I do measurement, it becomes unravelings. And so that works for me, but of course, it's opposition to many world interpretation and other interpretations, who, on the other hand, tell us what happens in the physical world. So I was not joking when I say I embrace them. I actually love every idea to find out what is happening in the microscopic world. I do not like the fact that Copenhagen interpretation doesn't care what happens in the microscopic world at all. And that's what Bohr literally said to Einstein, that it doesn't bring me anything new I can use for experiments, so I don't even want to know what happens in the microscopic world. I'm sure that left Einstein grumpy. Yeah?
Thank you. For me, as an experimentalist, there's no way I have to think of the quantum wave function to be real, because when I tweak something in the lab, everything is following so nicely. But as you said, the different interpretations is just our ways to cope with it, and they cannot be proven wrong because the predictions are not different. But I had a very concrete question. In your slide where you talked about Weisskopf-Wigner, when you had these different parts of the wave function.
Sure, yeah.
The first one had a different energy. It was A as G and 0.
Yeah.
Is this photons which are emitted in other modes which you don't show?
No. So yeah, thank you, Gert. That's right. Okay, I've done that a little bit more efficiently.
Yeah, that's
right. That sum here is over the energy continuum and propagation directions and polarization degrees of freedom. And the calculation is, of course, very equivalent to Fermi's golden rule. So it does turn out that the decay rate depends only on the density of state on resonance. But the photons that come out do have a spectrum like the Lorentzian spectrum we saw earlier today. So because of the finite lifetime of the atom, it's perfectly consistent that the photon coming out does not have to have exactly the same energy. So some of these lambdas will be within that Lorentzian width, and they will be populated. Yeah, yes.
Okay, so this is a really, really interesting conversation. I feel really bad having to interrupt, but due to the interest of time, I'll have to defer further questions to the coffee break. So let's all thank Klaus again.